Welcome to Sleepy Crimes. I am Anna, your host. Tonight, we drift into the shadows of seafloor spreading and the lonely journey of a man who saw the world move when everyone else insisted it stood still. Imagine, if you will, a study lined with heavy oak bookshelves, the air thick with the scent of old parchment and beeswax. A single lamp casts a warm, amber glow over a sprawling map of the world, its edges curled and yellowed by time. Outside, a gentle rain taps a rhythmic, soothing pattern against the glass, a soft lullaby for a world that feels solid, grounded, and permanent. But beneath this stillness lies a story of upheaval, a theory that once seemed as impossible as the mountains walking across the sea. We begin our journey in the early years of the 20th century, a time of rigid certainties and quiet scientific cloisters, where the ground beneath our feet was thought to be eternal and unmoving. In the year 1912, the scientific world was a landscape of tradition and deep-seated conviction. Geologists of the era were largely what we call fixists. They believed that the continents and the deep ocean basins were permanent features, etched into the crust of the planet since the very beginning of time. To them, the Earth was a cooling sphere, contracting and wrinkling like a drying apple, with mountain ranges forming as the skin of the world tightened. It was a comfortable, static view of existence. There was a profound sense of order in the idea that the ground beneath one's feet had always been exactly where it was. Change was thought to be vertical, islands sinking, or mountains rising, but never horizontal. The idea of a continent sliding across the face of the globe was not just considered wrong. It was seen as a breach of common sense, a flight of fancy that belonged more in a dream than a laboratory. On the 6th of January, 1912, a young meteorologist named Alfred Wegener stepped into the Great Hall of the Senckenberg Museum in Frankfurt. He was 31 years old, a man with a trim mustache and an outsider's perspective. He had not come to talk about the weather, as many expected. Instead, he stood before the German Geological Association to propose something radical. He spoke for nearly an hour, his voice steady as he described a world that was once united. He spoke of a supercontinent he would later name Pangaea, meaning all lands. He suggested that the Atlantic Ocean was not a permanent void, but a widening rift. The room was filled with men who had spent their lives cataloging the stillness of the earth, and as Wegener spoke, the air in the hall grew cold. There was no applause when he finished. There was only the sound of muffled whispers and the heavy, judgmental silence of the establishment. Wegener's inspiration had come from a simple observation that many had noticed, but few had dared to explain. He had looked at the coastline of South America and the western edge of Africa and saw how perfectly they seemed to nestle into one another, like two pieces of a grand, planetary jigsaw puzzle. But he went deeper than the visual fit. He spoke of the Mesosaurus, a small, freshwater reptile whose delicate fossils were found in both Brazil and South Africa. This creature, no larger than a hound, could never have survived a journey across 3,000 miles of salt water. His critics argued that there must have been ancient land bridges, narrow strips of stone that once spanned the oceans like bridges of lace, only to sink beneath the waves. Wegener, however, looked at the density of the rocks and argued that these bridges could not simply vanish into the deep. He proposed a simpler, yet more terrifying truth: the land had moved. The reception was brutal and unforgiving. Wegener was a meteorologist, an interloper in the sacred, dusty halls of geology. The experts of the day called his theory a beautiful dream, the product of a wandering mind. They mocked his lack of a mechanism, the engine that could possibly move a continent. How could a massive slab of granite plow through the solid floor of the ocean? At the time, they believed the mantle was as rigid as steel, an immovable foundation that would crush any landmass attempting to sail through it. Wegener suggested the forces of the Earth's rotation or the pull of the moon might be responsible, but the math did not hold. His colleagues calculated that these forces were far too weak, millions of times too small to nudge even a single mountain. And so, without a motor to drive his theory, Wegener was cast into a long and bitter scientific exile. His ideas were relegated to the margins, dismissed as unscientific. For decades, the theory of continental drift remained a ghost, whispered about in the back of classrooms but never invited to the podium. This was the era of the Great Silence, a time when the truth lay hidden in the deep, dark waters of the Atlantic, waiting for a new generation to find the evidence Wegener could only imagine. As we linger here in the quiet of this early 20th century evening, we feel the weight of that rejection, the cold isolation of a man who saw the truth too soon. The fire he lit would smolder for years, unheeded, until the sea itself began to speak. We leave him there in the silence of 1912, as the rain continues its steady, hypnotic rhythm against the glass. Sleep now, while the world slowly shifts beneath you. Our journey into the deep has only just begun. Close your eyes, breathe deeply, and listen to the pulse of the ancient, moving earth. The silence that had settled over the theory of continental drift was not a peaceful one. It was a period of stagnant uncertainty, where the vast oceans were still viewed as immutable barriers, frozen in time and space. But as the 1940s dawned, the world was thrust into a conflict that would change everything, including our understanding of the very ground beneath our feet. The Second World War was a time of immense tragedy, but also of frantic innovation. Out of the necessity of naval warfare, a new way of seeing the world was born. Scientists and sailors were no longer content to simply skim the surface of the wine-dark sea. They needed to know what lay beneath the waves, hidden in the crushing pressure and absolute darkness of the abyss. This necessity would eventually provide the eyes that geology had so desperately lacked, turning the invisible depths into a map of revelation. Imagine standing on the deck of the United States ship Cape Johnson, an attack transport vessel cutting through the Pacific waters in 1945. The air is thick with the scent of salt and diesel, and the steady vibration of the engines hums through the soles of your boots. Among the crew is a man named Harry Hess, a geology professor from Princeton University, who has traded his tweed jacket for a Navy uniform. While his primary mission involves the movement of troops to battlefronts like Iwo Jima and the Marianas, his scientific mind never rests. Hess possessed a curiosity that could not be dampened by the chaos of war. He convinced his crew to keep the ship's echo sounding equipment running 24 hours a day, even when they were far from the shallow dangers of the coastline. He was listening to the heartbeat of the deep, waiting for the ocean to whisper its secrets back to him. The technology at his fingertips was sonar, an acronym for sound navigation and ranging. It was a deceptively simple concept rooted in the rhythm of an echo. From the hull of the Cape Johnson, an electronic pulse, a sharp and lonely ping, would be sent downward into the blackness. This sound wave would travel through the water at roughly 1,500 meters per second, a ghost of a sound searching for a surface. When it finally struck the seafloor, it would bounce back, returning to the ship as a faint, ethereal memory. By measuring the exact time it took for that sound to make its round trip, Hess could calculate the depth of the water with unprecedented precision. It was like a blind man tapping a cane against the floor of a darkened cathedral, slowly, painstakingly, beginning to sense the shape and scale of the room he was standing in. Before these systematic surveys, the scientific community largely believed the seafloor was a featureless, flat desert, a vast plain of ancient mud that had remained undisturbed for billions of years. They imagined it as a graveyard of history, where the dust of ages settled in thick, heavy layers. But as Hess watched the paper scrolls of the echo sounder, a different picture began to emerge. The needles danced with a frantic energy, tracing lines that were anything but flat. Instead of a smooth basement, the sonar revealed a world of jagged peaks, deep valleys, and strange, flat-topped mountains that Hess called geos. These geos were particularly haunting. They looked like volcanic islands that had been decapitated and drowned, sinking thousands of feet below the surface. The seafloor was not a stagnant wasteland. It was a rugged, mountainous landscape that rivaled the grandest ranges on the dry continents. As the Cape Johnson traversed the Pacific, the data continued to pour in, painting a portrait of a world that defied all previous logic. Hess noticed that the mid-ocean ridges were not just isolated mounds, but part of a continuous, winding chain of mountains that seemed to encircle the entire globe like the seams on a baseball. These ridges rose thousands of meters above the abyssal plains, their summits often scarred by deep rifts. The sheer scale of this discovery was staggering. It suggested that the ocean floor was not a passive container for the world's water, but a dynamic and active participant in the Earth's architecture. The echoes bouncing off the floor were telling a story of movement and power, of a landscape that was far more youthful and violent than anyone had dared to imagine during those long, quiet years of geological skepticism. Perhaps the most baffling revelation came from the texture of the evidence itself. If the oceans had truly existed for 4 billion years, the sediment layers should have been miles thick, a deep accumulation of cosmic dust and organic remains. Yet the sonar and subsequent seismic tests revealed that the sediment was startlingly thin. It was as if someone had swept the floor recently, leaving behind only a few hundred meters of debris. This inconsistency gnawed at the minds of researchers. Where was the missing time? Why was the deep ocean floor so much younger than the continents it bordered? These questions were the echoes of a new era. The ghost of continental drift was beginning to take on a solid, mountainous form. The abyss was no longer a silent void. It was a witness, and it was finally starting to speak in a language of pings and pulses that no scientist could ignore. The year is 1948, and the air inside the Lamont Geological Observatory in New York is thick with the scent of old paper, tobacco, and the ozone of early electronic equipment. While the world outside is busy rebuilding from the scars of war, a quiet revolution is taking place on a drafting table. Marie Tharp sits here, surrounded by reams of paper that stretch out like endless, unrolled scrolls. She is a woman of immense patience and singular focus, a geologist who is forbidden from stepping foot on the very research vessels that collect her data. In those days, a woman on a ship was considered a harbinger of bad luck, a superstition that kept Marie anchored to her desk. But while her partner, Bruce Heezen, sails across the turbulent North Atlantic, Marie is doing something perhaps even more daring. She is listening to the echoes of the deep and translating the sound of the dark into a language of lines and ink. Imagine the ship, the Vema, cutting through the gray swells of the ocean. Beneath its hull, a transducer sends out a sharp ping of sound. It travels down through 1 mile, 2 miles, 3 miles of crushing, freezing water until it strikes the floor and bounces back. This is sonar, a technology born from the desperate need to hunt submarines during the war, now turned toward the mystery of the Earth itself. On the ship, these pings are recorded as simple numbers or jagged lines on long rolls of paper. To the sailors, they are just depths, a way to ensure the keel doesn't scrape a hidden rock. But when these rolls arrive at Marie's desk, they become something else. She begins the painstaking process of plotting these points, one by one, across thousands of miles of empty sea. She uses a technique called vertical exaggeration, stretching the heights of the underwater features by 20 times their actual scale so that the subtle textures of the Earth become visible to the human eye. By 1952, Marie has begun to notice a pattern that defies every geological textbook of the era. As her pen scratches across the paper, she connects the dots from 6 different transatlantic crossings. A mountain range begins to emerge from the abyss, a massive, rugged spine that seems to split the Atlantic Ocean right down the middle. But it isn't just a mountain range. At the very crest of these peaks, Marie identifies a consistent, deep, V-shaped notch. It is a cleft in the earth, miles wide and hundreds of feet deep, running continuously along the center of the ridge. To Marie, this look is unmistakable. It resembles the Great Rift Valley in East Africa, a place where the earth is literally pulling itself apart. She realizes she is looking at a wound in the planet, a place where the crust is splitting. If this is true, it means the continents are not fixed. It means they are moving. When she shows her findings to Bruce Heason, the reaction is not one of celebration. Bruce is a man of his time, and the idea of continental drift is considered scientific heresy, a fringe theory that most serious geologists have laughed out of the room. He looks at Marie's meticulous drawings and dismisses them with a phrase that would haunt the annals of science. He calls it girl talk. He tells her to go back, to recalculate, to find the error that must surely be hiding in her measurements. For nearly a year, Marie works in a kind of professional exile at her own desk, replotting the data, refining the curves of the undersea canyons, and tracing that central rift with even greater precision. She doesn't argue with words. She argues with the ink. She knows that the shapes she is seeing are real, and she waits for the rest of the world to catch up to the truth hidden in the shadows of the sea. The turning point arrives from an unexpected neighbor. At the desk right next to Marie's, a researcher named Howard Foster is working on a different project for Bell Laboratories. He is plotting the locations of undersea earthquake epicenters to help the company find the safest paths for the first transatlantic telephone cables. One afternoon, they decide to lay Howard's map of earthquakes over Marie's map of the seafloor. The result is electric. The clusters of earthquakes do not just happen randomly. They follow the exact path of Marie's Rift Valley with terrifying accuracy. The quakes are the sound of the earth breaking along the very line she discovered. Bruce can no longer ignore the evidence. The correlation is too perfect to be a coincidence. The rift is real, the earthquakes are the proof, and the entire foundation of geology is about to be shaken to its core. In 1957, they finally published their first comprehensive physiographic diagram of the North Atlantic. Because of the Cold War, the Navy has classified all traditional topographic maps of the seafloor, fearing that Soviet submarines might use the depth contours to hide. To bypass this, Marie and Bruce use a more artistic, three-dimensional style of sketching the terrain, as if viewed from a low-flying aircraft. This map is a masterpiece of both science and art. It reveals a world that no one had ever imagined, a landscape of jagged peaks, vast abyssal plains, and that central, life-giving rift. When the map is presented at Princeton, the head of the geology department tells Bruce that he has shaken the very foundations of their science. Marie Tharp, the woman who was never allowed to go to sea, has just mapped the dark and found the heartbeat of a moving world. Imagine the quiet of Lamont Hall in the late hours of 1952. The air is thick with the scent of old paper, the sharp, metallic tang of ink, and the steady, rhythmic hum of the building's furnace. Marie Tharp sits at her desk, a small island of yellow lamp light in a sea of encroaching shadows. Outside, the Hudson River flows silently through the night, but on her desk, a different sort of current is moving. She is surrounded by massive rolls of paper, hundreds of feet of sonar soundings brought back by Bruce Heason and the crew of the research vessel Vema. Because she is a woman, she is not allowed on the ship. The Navy rules of the time are rigid and unyielding. She is a shore-bound explorer, navigating the dark depths through the echoes recorded by men. Her fingers trace the jagged lines of the Atlantic floor, translating the pulses of sound into a physical landscape. The work is slow, repetitive, and deeply hypnotic. Each point she plots is a tiny piece of a puzzle that has remained hidden for millions of years in the crushing pressure of the deep. As she works through the middle of the North Atlantic, she begins to notice something strange. She is looking at the mountains, the massive underwater peaks that rise from the abyssal plains like the spines of sleeping giants. But as she meticulously sketches the cross-sections, a pattern emerges that defies the logic of the time. In the very center of the ridge, there is a deep, consistent indentation. It is a massive canyon, a valley that seems to mirror the mountain peaks on either side. It is a V-shaped scar, thousands of feet deep and miles wide, running right through the spine of the ocean. She pauses, the scratch of her pen stopping in the silence of the lab. She checks her math, then checks it again, her eyes scanning the long columns of numbers. The feature is not an error in the sonar or a glitch in the equipment. It is real. It is a wound in the Earth's crust, stretching as far as her data will allow her to see. She realizes in a moment of clarity that this is not just a mountain range. It is a rift. It is the place where the world is being pulled apart. When Bruce Heezen returns from his latest expedition, the atmosphere in the lab shifts. He is a man of action, a scientist who believes in what he can touch and see from the salt-sprayed deck of a ship. When Marie shows him her drawings and points to the Central Valley with a steady hand, the air grows heavy and tense. At this time, the idea of continental drift is considered a scientific joke, a heresy proposed by Alfred Wegener decades earlier that most geologists dismissed as impossible. To suggest the seafloor is pulling apart is to suggest the continents are moving, a concept that Bruce finds intellectually offensive. He looks at her work, groans with frustration, and dismisses her discovery with a phrase that would echo through history as a testament to the era's deep-seated prejudice. He calls it girl talk. He tells her to go back to the beginning, to redo every chart, to find the mistake that surely must exist in her calculations. He cannot accept that a woman at a desk has found the crack in his world. Marie does not argue. She does not raise her voice against his dismissal. She simply works. She spends months recalculating, replotting, and refining her maps with a focus that is as cold and deep as the ocean itself. She is a master of patience, letting the data speak where her voice cannot. While Bruce focuses on the visible mountains, Marie focuses on the silence between them. Soon, a second set of data arrives in the lab from an adjacent desk. A young researcher named Howard Foster is plotting the epicenters of earthquakes across the globe. When Marie takes his map of seismic activity and overlays it onto her own topographical sketches, the truth becomes undeniable. The earthquakes are not scattered randomly across the vast Atlantic. They fall in a perfect, jagged line directly within the central rift valley she has discovered. The tremors of the earth are coming from the very heart of the wound. The mountains are shaking because they are being born, and the earth is screaming as it tears itself open. Seeing the earthquake data finally breaks the walls of Bruce's skepticism. The coincidence is too great, the alignment too perfect to ignore. He realizes that Marie has found the smoking gun of a planetary revolution. By 1953, he begins to accept that the mid-ocean ridge is not just a local feature, but a global system. It is a 40,000-mile-long chain of volcanic mountains with a crack running down its center like the seam of a baseball. When he eventually presents these findings to the scientific community in 1957, the reaction is one of profound shock. Harry Hess, a preeminent geologist of the age, famously tells Bruce that he has shaken the foundations of geology. Yet, for a long, painful time, Marie's name is left off the official papers. She remains in the shadows of the laboratory, her hands stained with the ink of a discovery that has changed everything we know about our home. She is the silent architect of a new Earth, watching from the sidelines as the world begins to grasp the magnitude of the rift. The mystery of the Rift Valley even draws the attention of the famous explorer Jacques Cousteau. Doubting the existence of such a massive, hidden feature, he takes his ship, the Calypso, to the middle of the Atlantic. He lowers a deep-sea camera, expecting to find nothing but smooth, sediment-covered slopes. Instead, the flickering footage reveals a terrifying, beautiful reality. The camera captures the jagged, vertical walls of the rift, the fresh, black lava flows, and the sheer, dizzying scale of the abyss Marie had mapped from her desk in New York. The world is finally forced to look into the wound. We are living on a planet that is constantly renewing itself, pushing the old floors aside to make room for the new. As you drift towards sleep, imagine that deep, dark valley in the center of the ocean. It is a place of endless creation, a slow-motion explosion of life and rock, pulsing in the absolute silence of the deep. The earth is breathing, moving, and stretching beneath you. Everything is in motion, even as you find your rest in the quiet of the night. We leave the churning wake of physical exploration and step into a quieter space, one of dusty bookshelves and the rhythmic clicking of a typewriter in the dead of night. The year is 1960. We are in a small office at Princeton University. Outside, the world is changing, but inside these walls, a man named Harry Hess is quietly dismantling everything we thought we knew about our planet. Harry is not just a geologist. He is a man of the sea, a rear admiral who spent the long, tense hours of the Second World War staring at the glowing screens of sonar equipment. As he moves his pen across the page, the ink seems to flow like the dark waters he once surveyed. He is about to release a manuscript that will change history, but he does so with a strange, humble warning that its contents are more imagination than established fact. Harry Hess understood the ocean floor in a way few others could. During his time commanding the USS Cape Johnson, he never truly stopped being a scientist. While his ship cut through the Pacific, he kept the sonar running, mapping the strange, flat-topped mountains he called geos. He saw the deep, jagged trenches that looked like scars on the Earth's face. By 1960, these memories had coalesced into a vision. He saw the Earth not as a static, frozen orb, but as a living, breathing machine. However, there was a problem. The evidence he had was fragmented, ghostly echoes from a sonar machine, and the puzzling youth of the ocean rocks. He was a detective at a crime scene where the primary suspect had already fled, leaving behind only the faintest traces of movement. To bridge the gap, he turned to something unexpected, the language of the soul. He titled his seminal paper, The History of Ocean Basins, but in the very first paragraphs, he made a move that baffled his more rigid colleagues. He called his work an essay in geopoetry. Imagine that for a moment. The cold, hard science of geology described as poetry. He used this word because he knew he was stepping into the realm of the imagination. He was asking his readers to suspend their disbelief, to look past the missing data and see the beauty of the system he was proposing. At the time, the hard proof, the fingerprints of the deep, was still largely missing. He was painting a picture of a world in motion without being able to show the brushstrokes. It was a leap of faith, a narrative built on the slender threads of intuition and the hauntingly deep valleys he had seen from the deck of his ship. In this geopoetry, Hess described a magnificent conveyor belt. He imagined the great mid-ocean ridges as the birthplace of the world. Here, deep within the mantle, heat was rising in slow, majestic convection cells. As this molten rock reached the surface, it would ooze out into the freezing water, hardening into new crust. This new floor would then begin a slow, inevitable journey away from the center, pushed aside by the next pulse of magma. It was a process of constant creation, a shimmering birth occurring in the pitch-black silence of the abyss. But if the Earth was growing in the center, it had to be shrinking elsewhere. Hess turned his gaze to the deep trenches, those dark pits at the edges of the continents. Here, he proposed, the old crust was finally sliding back into the Earth's fiery heart. This was the cycle of the seafloor, born at the ridges, dying in the trenches. It was a radical idea that finally explained why the ocean floor was so young. While the continents held rocks billions of years old, the seafloor was a mere infant, rarely older than 200 million years. But in 1960, this was still just a story. The magnetic stripes that would eventually prove him right had not yet been fully deciphered. The ocean was still a vault, its secrets locked behind miles of crushing pressure and absolute darkness. Hess was like a narrator describing a phantom, a ghost that moved the continents like heavy rafts on a slow-moving river. He was telling us that the very ground beneath our feet was a traveler, moving at the speed that a fingernail grows, silent and unstoppable. The scientific community was hesitant. They were used to facts they could touch, measurements they could verify with a ruler. Hess offered them instead a vision of a planet that recycled itself, a world that was constantly erasing its own history. As he sat in his office, the lamplight casting long shadows across his maps, he knew his geopoetry would either be his greatest legacy or a beautiful fantasy. He was waiting for the light to hit the crime scene, for the technology to catch up to his imagination. For now, the deep remained a place of mystery, a vast, dark canvas waiting for the first streaks of color to appear. The poetry was written, the proof would have to wait. The silence of the deep still held its secrets, while on the surface, the whispers of a revolution began to grow. Harry Hess had given the world a map of the imagination, a poem of moving earth. But scientists, by their very nature, are hungry for the tangible. They need the weight of a measurement and the certainty of a repeating pattern. In the early 1960s, two men at Cambridge University were about to find that pattern hidden in the cold, dark basalt of the deep sea. Frederick Vine, a young student full of curiosity, and his supervisor, Drummond Matthews, were not looking for a revolution. They were looking at data, trying to make sense of the erratic whispers coming from the bottom of the Indian Ocean. The setting was far from the dramatic waves of the open sea. They worked in a converted stable at Cambridge, a quiet, dusty space where the air smelled of old paper and the blue ink of fountain pens. It was 1962 and 1963, a time when the world was changing, yet the secrets of the earth remained locked beneath miles of salt water. They spent many hours leaning over heavy wooden tables, smoothing out long rolls of paper filled with jagged, ink-drawn lines. These lines were magnetic readings, captured by ships that had crisscrossed the Carlsberg Ridge, a jagged underwater mountain range in the northwest Indian Ocean. Imagine the ship, the HMS Cook, tossing on the restless, gray surface of the Indian Ocean. Behind it, a long, heavy cable trailed through the salt water, pulling a device called a magnetometer. This instrument was like a sensitive ear, listening to the magnetic heartbeat of the rocks far below the hull. As the ship moved with the rhythm of the waves, the device recorded the strength and direction of the magnetism trapped in the crust. To any other eye, the resulting graphs might have looked like noise, meaningless zigzags of ink on a page. But to Vine and Matthews, there was a rhythm emerging from the depths, a symmetry that seemed almost too perfect to be true. When they looked at the charts, they did not see randomness. Instead, they saw stripes. Imagine a zebra's coat laid out across the vast, dark ocean floor. There were bands of high magnetic intensity followed by bands of low intensity. These stripes ran parallel to the central ridge, stretching out for miles like a giant, geological barcode. The most startling discovery was that the pattern on the left side of the ridge was a perfect mirror image of the pattern on the right. If there was a wide stripe 10 miles to the east, there was an identical wide stripe 10 miles to the west. It was as if the Earth were printing its history in two directions at the same time. To understand why this was happening, we must consider the nature of the Earth itself. Our planet is a giant magnet, but it is a restless one. Every few 100,000 years, the North and South Poles decide to trade places. In the early 1960s, this idea of geomagnetic reversal was still fresh and very controversial. Vine and Matthews realized that as the hot, molten rock rose up from the ridge, it acted like a wet, impressionable clay. As it cooled into solid basalt, the tiny iron minerals inside aligned themselves with the Earth's magnetic field, whatever it happened to be at that moment. Once the rock hardened, that direction was frozen in time, locked away from the world. This was the final missing piece of the puzzle. The seafloor was not just a floor, it was a giant tape recorder. As the conveyor belt of the crust moved away from the ridge, it carried the magnetic signature of its birth with it. When the Earth's field flipped, the next batch of rock recorded the new direction. The symmetrical stripes were the physical proof that the seafloor was spreading from the center, pushing older rock aside to make room for the new. It was a slow, majestic process, a dance of minerals and magnetism that had been occurring for millions of years. They published their findings in September of 1963, and though the scientific world was initially slow to listen, the evidence was undeniable. The magnetic fingerprint was the smoking gun. It turned the geopoetry of the past into hard, measurable fact. It proved that the continents were not just drifting through the water, but were part of a massive, interconnected system of moving plates. As the night deepens, think of that ancient machine beneath the waves, the rhythmic flipping of the poles, and the stripes of stone that tell the story of our planet's restless heart. As the conveyor belt of the crust moved slowly away from the central rift, it carried with it a secret, etched into the very atoms of the stone. Imagine for a moment that you are standing on the deck of a research vessel in the year 1963. The air is sharp with the scent of salt and the damp chill of the North Atlantic. Beneath you, the ocean is a vast, unblinking eye of dark indigo, hiding a landscape more rugged than any canyon on land. You are part of a team of scientists, including young men like Frederick Vine and Drummond Matthews, who are dragging a heavy metal cylinder called a magnetometer behind the ship. It bobs in the wake, tethered by a long cable, quietly sensing the invisible forces of the planet. As the ship glides over the Reykjanes Ridge near Iceland, a rhythmic clicking fills the cabin. A stylus dances across a scrolling roll of paper, leaving behind a jagged trail of ink. At first, it looks like a chaotic heartbeat, but as the miles of water pass beneath the hull, a startling regularity begins to emerge from the noise. This was the birth of the zebra stripes. The data did not show a uniform magnetic field across the ocean floor, as many had expected. Instead, the magnetometer revealed a series of long, linear bands of alternating magnetic intensity. Some stripes pulled strongly toward the north, matching the world as we know it today. These were followed by stripes where the magnetic pull was strangely weak, almost as if the Earth's magnetism was being canceled out by something deep within the crust. It was a pattern so precise, so orderly, that it seemed almost artificial. These stripes were perfectly parallel to the mid-ocean ridge, stretching for hundreds of miles across the lightless plains of the abyss. To the eyes of Vine and Matthews, and to the Canadian geophysicist Lawrence Morley, who was independently reaching the same conclusion, these were not just random wiggles on a page. They were the signatures of time itself. To understand what these stripes truly represent, we must look closer at the birth of the rock. At the center of the ridge, the Earth is bleeding. Red-hot magma rises from the mantle, squeezing through the cracks in the crust to meet the freezing touch of the deep sea. As this lava cools and solidifies into basalt, something miraculous happens. Within the molten stone are millions of tiny crystals of a mineral called magnetite. These crystals are rich in iron, and while the lava is still liquid, they are free to pivot and turn like microscopic compass needles. They align themselves perfectly with the Earth's magnetic field at that exact moment in history. Once the rock cools past a certain point, known to scientists as the Curie point, these tiny needles are frozen in place. They become a permanent record, a stone-cold memory of where North and South lay on the day the rock was born. But the Earth is a restless creature. Every few 100,000 years, for reasons that still baffle the greatest minds in science, the planet's magnetic poles undergo a total reversal. What was once north becomes south, and what was once south becomes north. When this happens, the new lava erupting at the ridge records the new direction. This is why the stripes alternate. A band of normal polarity is followed by a band of reversed polarity, creating a grand, monochromatic tapestry across the seabed. It is as if the Earth is a giant tape recorder, and the mid-ocean ridge is the recording head. As the seafloor spreads outward, it preserves the history of the planet's magnetic heartbeat. One stripe might represent a period of 500,000 years, while the next represents 2 million. They are the pages of a book, written in the language of magnetism. The most beautiful part of this discovery, the part that finally silenced the skeptics, was the symmetry. If you were to start at the very center of the ridge and travel 10 miles to the east, you would see a specific pattern of wide and narrow stripes. If you then returned to the center and traveled 10 miles to the west, you would find a perfect mirror image of that same pattern. The sequence of stripes on one side of the ridge was identical to the sequence on the other. This was the smoking gun. In 1966, when Walter Pittman analyzed a magnetic profile from the Pacific-Antarctic ridge known as Elton 19, the symmetry was so flawless it was undeniable. It proved that the seafloor was not staying still. It was moving, growing, and pushing the continents apart at a rate of just a few centimeters every year. The ocean was not an ancient, stagnant basin. It was a dynamic, living skin, constantly renewing itself at the center and sliding away into the dark. Think of the immense power required to move an entire ocean floor. It is a process so slow that a human life is but a blink in its progress, yet it is powerful enough to reshape the very map of our world. Each stripe of rock is a testament to the passage of eons, a silent witness to the era when the Atlantic was just a narrow river, and the mountains of Africa were joined to the hills of the Americas. The zebra stripes told us, once and for all, that the ground beneath our feet is a traveler. We are all drifting on a great conveyor belt of stone, riding the waves of a subterranean sea of heat. As we sit here in the quiet of the night, miles below us, the magnetite needles are still locking into place, recording the story of today for the scientists of 1,000,000 years from now. The tape is still rolling, the floor is still spreading, and the mystery of the Earth continues its slow, majestic journey into the light. The year 1968 marked a turning point in our understanding of the world beneath the waves. While much of the human gaze was fixed upward toward the moon, a different kind of pioneer was preparing to descend into the abyss. This was the voyage of the Glommer Challenger. Her most striking feature was the steel derrick rising 43 meters above her deck, a skeletal finger pointing toward the sky while her true purpose lay miles below the hull. As she left the shipyard in Orange, Texas, and made her way into the vast swells of the South Atlantic, she carried more than just drilling equipment. She carried the weight of a theory that had split the scientific community for decades. Harry Hess had proposed seafloor spreading, but ideas require physical proof, and the Glommer Challenger was built to find it. Imagine standing on the deck of this 400-foot vessel in the middle of the ocean. There are no landmarks, only the endless blue horizon and the deep, rhythmic pulse of the engines. To drill into the seafloor miles below, the ship had to remain perfectly still in the shifting currents. The crew used a groundbreaking system of dynamic positioning. They dropped acoustic beacons to the ocean floor, which whispered signals back to the ship. Computers used those signals to control thrusters on the hull. The sound of these thrusters was a constant hum, a background melody to the work of the scientists who were about to peer into the very crust of the Earth. It was a technological marvel, a platform of stability in an environment that was never meant to be stationary. The process of drilling was a slow, deliberate dance. Section by section, the crew connected lengths of heavy drill pipe, lowering the string through the moon pool, a central opening that led directly into the water. Thousands of feet of pipe eventually dangled like a thin wire in the cold depths. As the drill bit finally touched the sediment on the seafloor, miles beneath the keel, a vibration traveled back to the surface. It was a tactile connection to a world untouched for millions of years. The drill would grind into the soft silt and hit the hard, dark basalt beneath. In the quiet night, the rhythmic clanking of the machinery told the story of a journey through time, penetrating layers of history with every foot of progress into the deep, dark layers of the Atlantic. When the first cores were brought to the surface, the atmosphere on the ship was electric. These were 30-foot-long cylinders of history, encased in plastic liners and hauled from the depths. As the scientists split them open, they saw a vertical timeline of the planet. The top layers were soft, pale oozes made of microscopic shells. But as they looked deeper, the material changed. It became denser, darker, giving way to the solid, black volcanic rock of the basaltic crust. The smell was unique, a damp, mineral scent of ancient earth and salt sealed away from oxygen for eons. Each core was a physical piece of evidence, a tangible link to the processes occurring far beneath the mud, pulled into the bright light of day for the first time in human history. During the famous third leg of the expedition, between December 1968 and January 1969, the crew drilled 17 holes across the mid-Atlantic ridge. The results were undeniable. As they moved further from the central ridge, the age of the basalt grew older in a perfect, symmetrical pattern. Near the ridge, the rock was young and fresh. Further away, the basalt was tens of millions of years old, buried under thick blankets of ancient silt. It was the smoking gun for seafloor spreading. The ocean floor was not a static basement, but a conveyor belt constantly being borne at the ridges and pushed toward the continents. This discovery confirmed that the Earth was dynamic, constantly renewing itself in the dark, silent places where no sunlight ever reaches. The data collected by the Glommer Challenger transformed our vision of the Earth. It confirmed that the Atlantic Ocean had widened over 200 million years. The floor of the sea was a restless thing, moving at the speed that a fingernail grows, yet powerful enough to shift entire continents. As the ship moved through the dark waters, the crew knew they had rewritten the textbooks. The mystery of the moving Earth was no longer just a theory. It was written in the cold, hard stone they had pulled from the darkness. The shadows of the deep had finally begun to yield their secrets to the light of science, and the world would never look the same again. We had finally reached through time itself, touching the foundations of our wandering planet. As the heavy steel drill string lowered into the dark abyss of the South Atlantic, the crew of the Glommer Challenger worked under a sky that seemed to stretch into eternity. This was the third leg of their mission, a journey that would forever change our understanding of the ground beneath our feet. The ship was a marvel of engineering, a floating laboratory that could hold its position against the restless currents of the open sea using a system of sophisticated thrusters. On the deck, the sound of the machinery was a rhythmic, industrial lullaby, a constant hum that vibrated through the soles of the scientists' boots as they waited for the Earth to reveal its secrets. When the first core samples finally emerged from the depths, they were greeted with a hushed reverence. These were long, slender cylinders of history, encased in plastic tubes and dripping with the cold, pressurized water of the ocean floor. To the untrained eye, they were merely segments of mud and rock, but to the geologists, they were the pages of a lost diary, waiting to be read for the first time in millions of years. They began their forensic analysis with the sediment, the soft, pale layers of microscopic shells and silt that had settled like a slow-falling snow over vast stretches of time. Near the mid-Atlantic ridge, the scientists found that this layer was incredibly thin, a mere dusting of time upon the dark volcanic rock beneath. It was almost as if the Earth there was too young to have gathered any dust at all. But as they moved further away from the ridge, traveling toward the distant shores of Africa and South America, the sediment began to thicken. It grew from a few meters to hundreds of meters deep, a heavy blanket of time that spoke of a long and quiet accumulation. Within these layers were the tiny remains of prehistoric organisms, microfossils known as foraminifera, which acted as biological markers. By identifying the specific species of these creatures, the paleontologists could determine the age of the very first layer of sediment that had touched the basalt floor. It was a clear, unmistakable pattern. The farther they sailed from the central ridge, the older the fossils became. But the true confirmation lay deeper, within the basaltic crust itself. The scientists used the precision of radiometric dating to unlock the chronological secrets held within the volcanic rock. They looked at the radioactive isotopes trapped inside the minerals, atoms like potassium that slowly and predictably decay into argon over vast stretches of time. This was the geological clock, an invisible, steady ticking that could not be hurried or slowed. Inside the ship's laboratory, surrounded by the smell of salt and the sterile scent of scientific equipment, they measured these ratios with meticulous care. As they tested the samples from the 17 holes drilled at 10 different sites, the data painted a stunning and undeniable picture. The rock at the very center of the ridge was practically brand new, fresh from the Earth's molten interior and still holding the heat of its creation. It was less than 5 million years old, a mere blink in the eyes of the universe. As the research vessel moved outward toward the continental margins, the clock revealed ages that reached back 100 million, then 150 million, and finally nearly 200 million years. This was the clinching evidence that the scientific community had been searching for. The ocean floor was not a static, eternal basin that had existed since the dawn of the planet 4.5 billion years ago. Instead, it was a conveyor belt of constant renewal. At the ridges, new crust was being born in a slow-motion eruption of fire and ice, cooling against the seawater and beginning its long, silent journey away from the center. It was as if the Earth were a giant machine, recycling itself in the dark. This discovery explained why the ocean floor was so remarkably young compared to the continents. While the granite of the mainland might be billions of years old, the oldest piece of the Atlantic floor was barely 200 million years old. The seafloor was a transient thing, a fleeting layer of the planet destined to eventually sink back into the mantle to be remelted. The scientists aboard the Glommer Challenger realized they were looking at a natural tape recording of our world. Each mile of the seafloor was a verse in a story of movement and change. The data from the South Atlantic did not just support the theory of seafloor spreading. It proved that the Atlantic Ocean had been growing for nearly 200 million years, pushing the continents apart at a rate of just a few centimeters every year. This is about the same speed at which a human fingernail grows, a pace so slow it is impossible to see, yet so powerful it moves entire worlds. In the quiet of the ship's laboratory, the reality of a living, breathing planet began to take hold. The Earth was not a cold, dead rock, but a dynamic system, constantly shifting and reshaping itself in the darkness of the deep. This forensic data turned a radical hypothesis into an undeniable truth, forever altering the map of our world. We now know that the ground beneath us is always moving, always growing, and always carrying us toward an unknown future, 1 centimeter at a time. The year was 1967, and the world was beginning to feel smaller. Not because of planes or radios, but because the very ground was finally being understood as a single, interconnected machine. In the quiet laboratories of Princeton and Cambridge, the air was thick with the scent of old paper and the low, steady hum of the very first computers. Imagine the scratch of a fountain pen across a heavy desk, the sound of a researcher leaning back in a wooden chair, exhaling slowly. The evidence from the deep sea had been trickling in for years, a slow drip of magnetic stripes and heat readings that refused to be ignored. But it was in this brief window of time that the drip became a flood. The investigation was no longer about local anomalies. It was about the final synthesis. Scientists were about to realize that the seafloor was not just a recording, but the very engine of the planet. At the heart of this shift were two men, Dan Mackenzie and Jason Morgan, working worlds apart but seeing the same invisible truth. They began to treat the Earth's crust not as a soft, flowing skin, but as a series of rigid, unyielding plates. Imagine a vast, ceramic puzzle covering a sphere. For years, geologists had tried to map these movements on flat sheets of paper, but the math never quite fit. Mackenzie and Morgan realized that to understand the world, they had to embrace the geometry of the sphere itself. They looked at the transform faults, those deep scars in the ocean floor, and saw them as the tracks along which these great plates rotated. It was a moment of profound clarity, like seeing the internal gears of a watch for the very first time. Each plate was approximately 100 kilometers thick, floating on a warmer, softer layer below, moving with a heavy, silent grace that defied human scales of time. By 1968, the French geophysicist Xavier Lepichon brought the power of the computer to the problem. He sat in the low light of a flickering screen, feeding in the data points gathered from every corner of the ocean. He was looking for a balance. If new crust was being born at the ridges, where was the old crust going? Through his analysis, the first truly global map of plate tectonics emerged. He identified 6 primary plates, massive sections of the Earth's shell that moved in concert. His work proved something essential. The Earth was not expanding like a balloon, as some had feared. Instead, for every inch of new floor created in the Atlantic, an equal amount was being consumed in the deep trenches of the Pacific. It was a perfect, closed system. The recycling of the world was constant, a slow-motion dance of creation and destruction that had been occurring for billions of years, hidden beneath the waves. The final, definitive proof arrived in the cold waters of the South Atlantic during late 1968. The research vessel Glomar Challenger was on its third leg, a journey specifically designed to test the spreading hypothesis once and for all. Imagine the heavy thud of the drill pipe as it lowered through 5 kilometers of dark water, seeking the secrets buried in the mud. They drilled 17 holes at 10 different sites, moving away from the mid-Atlantic ridge toward the coastlines. As each core sample was pulled onto the deck, the excitement was palpable. The results were undeniable. The farther they moved from the ridge, the thicker and older the sediments became. The fossils found at the base of the mud matched the magnetic ages perfectly. It was the smoking gun. The ocean floor was indeed a conveyor belt, and its age was no more than 200 million years, a mere blink in the 4.5 billion-year history of our planet. This was the new global tectonics, a title given by the community to a theory that finally explained everything. It explained why the mountains rose, why the volcanoes erupted in fiery arcs, and why the Earth shook in predictable patterns. The seafloor spreading that Harry Hess had dreamt of was now the cornerstone of a unified science. We could finally see the world as Alfred Wegener had glimpsed it in 1912, though with a complexity he could never have imagined. The continents were not plowing through the sea like ships. They were passengers on the plates themselves, carried along by the spreading floor. The mystery of the missing mechanism was solved. The heat from deep within the mantle was the fuel, and the ridges were the exhaust, pushing the world apart and pulling it back together in an eternal, rhythmic cycle. It is a quiet thought to consider how long the truth remained hidden. Alfred Wegener had died in the bitter cold of Greenland in 1930, a man whose ideas were often dismissed as eccentric or impossible. But in the late 1960s, the scientific community finally yielded. The ridicule of the past faded, replaced by a deep, respectful silence. The ghost of Wegener was finally at rest, his continental drift transformed into the elegant, mathematical reality of plate tectonics. The maps were redrawn, not just as static lines of geography, but as snapshots of a living, breathing entity. We realize that the ground beneath our feet is a traveler, and that the Atlantic Ocean, once a narrow rift, is still growing today, one fingernail's width at a time. The world had been synthesized into a single, beautiful whole. As the 1960s drew to a close, the revolution was complete. The investigation into the seafloor had revealed more than just mountains and trenches. It had revealed the heartbeat of the Earth. The deep sea is no longer a void, but a library of our planet's memory. We can look at the vast expanse of the oceans and feel a sense of peace, knowing the order that lies beneath the chaos of the waves. The plates continue their silent journey, the ridges continue to glow with new magma, and the Earth continues its slow, steady pulse. You can rest now, knowing that the great mystery has been solved, and the world is exactly as it should be. The case rests now. Let the details fade. You are safe. Close your eyes, breathe deeply, and have a good night. Sleep well. The world did not feel different to those walking upon its surface. Yet beneath the soles of their boots, the very foundations of the map were shifting. By the time the 1970s arrived, the scientific community had undergone a quiet, profound transformation. The mystery of the ocean floor was no longer a secret kept by the dark, cold depths, but a blueprint for understanding our home. We began to see the Earth not as a rigid, unyielding stone, but as a living, breathing entity, constantly recycling itself in a slow and rhythmic dance. Imagine the silence of the deep Atlantic, where the mid-ocean ridge continues its patient work, pushing the old world aside to make room for the new. It is a process that never sleeps, a restless energy that flows from the molten heart of the planet up through the cracks in the crust, cooling into fresh stone under the weight of 1,000 atmospheres. We have come to realize that the land we call permanent is merely a passenger on a slow-moving conveyor belt of rock. As we moved into the later decades of the 20th century, our vantage point shifted from the decks of rocking ships to the silent, airless void of space. We launched eyes into the sky, satellites that could peer down with impossible precision. These machines, orbiting hundreds of miles above the clouds, began to whisper to one another, bouncing signals across the vast reaches of the atmosphere. Through the use of very long baseline interferometry and the global positioning system, we gained the ability to measure the heartbeat of the continents with the accuracy of a single hair's width. We could finally see the invisible. We watched as North America drifted away from Europe, an inch at a time, measured by the time it takes for a radio wave to travel between two distant points. The data was clear and undeniable. The seafloor was still spreading, and the world was growing larger in some places while shrinking in others, all in a delicate, planetary balance that maintains the shape of our existence. There is a strange, quiet beauty in the pace of this movement. Scientists often describe the speed of the spreading as being roughly equal to the rate at which human fingernails grow. If you were to sit perfectly still on a beach in South Carolina, you would be moving away from the coast of Africa at a speed of perhaps 2 or 3 centimeters every year. It is a pace so deliberate, so glacial, that it escapes our senses entirely. Yet, over the course of a human lifetime, the Atlantic Ocean widens by the height of a person. Over the course of centuries, the gap grows by the length of a city block. In the Pacific, the movement is swifter, sometimes reaching 15 centimeters a year, a frantic race in geological terms. It is a reminder that the most powerful forces in nature do not always announce themselves with a roar. Sometimes, they operate in a silence so profound that it takes decades of careful observation from the stars just to notice the change in the horizon. Deep in the abyss, where no sunlight ever reaches, the legacy of seafloor spreading revealed even more wonders in 1977. Explorers descending in the small submersible named Alvin discovered the hydrothermal vents, towering chimneys of mineral-rich water spewing from the crust like black smoke. These are the exhaust pipes of the planet, where the heat of the mantle meets the freezing pressure of the deep sea. Around these vents, Life flourishes in ways we never thought possible, fueled not by the sun, but by the chemical energy of the earth itself. Giant tube worms and pale crabs huddle near the warmth of water that can reach 400 degrees Celsius, while just inches away, the ocean remains near freezing. It showed us that the restless movement of the plates creates more than just geography. It creates the conditions for life to survive in the most hostile environments imaginable. The seafloor is not a desert, but a garden fed by the inner fire of the world. We now live on a planet that we recognize as a puzzle of tectonic plates, always in motion. This understanding has changed everything, from how we predict the tremors of the ground to how we interpret the history written in the rocks of the highest mountains. The scars of the past are visible if you know where to look. The jagged peaks of the Himalayas are the result of a slow-motion collision between two massive landmasses, a process that continues to lift the mountains higher even as you listen to my voice. The restless world is not a place of chaos, but a place of incredible balance. For every bit of new crust born at the mid-ocean ridges, old crust is swallowed back into the mantle at the deep trenches, returning to the fire to be melted and eventually reborn in a cycle that spans millions of years. The Earth is a closed system, a masterpiece of recycling that ensures the surface is always being renewed, always changing, yet always the same home. As you lie here, safe and still, think of the immense scale of this clockwork. Beneath the blankets, beneath the floor, and deep beneath the soil, the great plates are sliding across the mantle. They carry the weight of the oceans and the pride of empires, all moving with the steady, unhurried rhythm of a deep breath. The earth is never truly still, yet there is a comfort in this constancy. The world renews itself, inch by inch, century by century, in a cycle that began billions of years ago and will continue long after we are gone. The maps of the future will look different than the maps of today, but the story will remain the same, a story of a planet that is vibrant, shifting, and profoundly alive. The case rests now. Let the details fade. You are safe. Close your eyes, breathe deeply, and have a good night. Sleep well.